Okay, guys, so on what day was that? Tuesday? We were talking about continuity. Continuity. Continuity basically means that you have a continuous line with no breaks in it or anything like that. But as soon as you have a breakage of some kind, we call that a point of discontinuity. All right? And then we found out that there are three things that have to occur for a function to be continuous at some point. So let's say at x equals c, I want to prove that my function's continuous there. Well, first thing that has to be true is that you should be able to plug c into your function and actually get an answer out. Okay? The next thing that should be true is that there should be a limit at that point. So if you approach x equals c from the left and from the right, they should meet at a common point. That limit should exist. The final thing that needs to be true is that those two things need to be equal. The actual y value of the function needs to equal the limit at that point. If all three of those criteria are met, then we have a continuous function at that point. Okay? If any of those things fail, then it's not continuous. Now, we're going to talk about all the different types of functions that you guys have ever learned about. And we're going to talk about where they are continuous and where they're not. Okay? So let's start off with polynomials. Polynomials are things like quadratic functions or polynomials. Anything where you have like a number x to a power plus a number x to a power, etc. Okay? Even linear functions are considered to be polynomials. They're always continuous. They're continuous from negative infinity to positive infinity, whether you're talking about parabolas or cubic functions or linear functions. They never have any holes, gaps, or jumps in them. So they're always continuous. They're never discontinuous. Okay? This sheet, by the way, you might want to make sure you put this like somewhere in your notebook, easy to grasp, because every once in a while throughout the year you're going to come back to this. Oh, okay. This worksheet again. Exponential functions is another thing you guys learned about. They look like this. Same thing. They have no holes, gaps, or jumps. They're continuous everywhere. They're continuous everywhere. Rational exponents are a little bit, rational functions, also known as, or any kind of quotient. In other words, anytime you have something over something else, they're not continuous everywhere. Anytime the denominator equals 0, that's a point of discontinuity because that's undefined at that point. Okay? So it would be continuous. If it's discontinuous here, that would mean it'd be continuous everywhere else, though. So if the bottom equals 0 at c, then your function is continuous from negative infinity up to c, and from c up to infinity, but not including c. Okay? So that's the continuity and discontinuity of a rational function. Square root functions. I'll make sure you guys' sheet looks like mine. I put radial. All right. Anyway. Radical functions are always continuous as well. But remember, radical functions look like this. So like they don't exist back here in the negatives anywhere unless you do some kind of transformation on them. But they are continuous anywhere where this guy underneath the radical is positive or equal to 0. So there are no points of discontinuity in that function so long as you're on that side of the graph. Okay. Odd roots, they tend to look like this, and they're always continuous. No points of discontinuity. Log functions. Let's talk about log functions. Log functions look like this. they're continuous as well. But remember, they only exist where the part you're taking the log of is greater than 0. Unlike this is a subtle detail we got to watch out for with square roots. They can equal 0, but with logs they can't. They're both greater than 0, but with logs it actually can't equal 0. So because it has a vertical asymptote. So it's continuous from anywhere where this is greater than 0 and on. So there you have it. Sine functions are continuous everywhere. Cosine functions are continuous everywhere. Tangent functions have little gaps all along the way. So let's talk about tangent functions. Same thing with cotangent, secant, and all of them. They have little gaps all along the way. Tangent tangent has gaps at pi over 2, and then every multiple of pi added to that afterwards. So at pi over 2, if you add pi to it, you're down here at 3 pi over 2. That's another gap. And then if you keep going around forever, that's where all the gaps will be. So for tangent, anytime the argument is at one of these places, that's a point of discontinuity. And that's the same thing for, I believe it's the same thing for secant as well, actually. Secant has the same thing, has the same gaps on it. Cosecant has gaps at every multiple of pi. So every time you get to a multiple of pi, there's a point of discontinuity. There's a vertical asymptote. Same thing for cotangent. Nobody's done the extra credit yet in here, so you guys probably don't recognize this right now, but that's the step function. Step functions look like this. Step functions are discontinuous anywhere where this part that's inside is equal to some integer. Like an integer is like 2, 3, 4, no fractions, just standard integers. Okay, so that's our reference sheet for the continuity of special functions that we'll be working with throughout the year. So you might want to keep that somewhere special. And in case you guys forgot, what we did last class was we were looking at continuity of functions on a graph. But now we're going to talk about continuity just by looking at an equation. And the only way you can really do that is with this sheet, knowing where it's continuous at and where it's not. So let's go ahead and do our first example then. Example 2. So we're going through this thought process here. Okay, now when you actually see these questions, they're either going to ask you one of two things. They're either going to say, where is it discontinuous at? Or they're going to say, where is it continuous at? But for us, we're going to just do both of those. But before you even do those, you kind of have to ask yourself, what kind of function is this? So look at your little sheet that I just gave you. Out of that list of functions that you see there, what kind of function is that? It's a rational function. So let's write that. Where is it discontinuous? So look at your rational function rule. Go over to the far right column. What does it say? All x for which, what was that last part? D of x equals 0. Now what does d of x represent? The bottom part, right? So I'm going to go ahead and erase this, and I'm going to put, what is my bottom part up there? Okay, so all x for which x squared minus 9 equals 0. So let's solve that. If we solve that, what do we get? And negative 3. 3 and negative 3. So this function would be discontinuous at 3 and at negative 3. So when you have a rational function, if you want to find where the function is discontinuous at, you just set the bottom equal to 0 and solve, and those are the two places where it would be discontinuous in this case, 3 and negative. So if my function is discontinuous at 3 and negative 3, the next question is, where is it continuous at? Okay, well, basically there's a hole here, there's a hole here in my graph. So it would be continuous from negative infinity up to negative 3, and then from negative 3 to positive 3, and then from 3 up to infinity. Okay? So we started by identifying what kind of function it is. Now that we know what kind of function it is, we could use that little sheet to find where it's discontinuous. Once you know where it's discontinuous, you can find where it is continuous. Okay? And why are we doing this once again? Because all calculus is based on limits, and limits really only work when a function is continuous, which means most of the theorems in calculus work only when a function is continuous. And they always try to sneak one sneaky problem in there where it's like they want you to use a rule, and it looks like, oh boy, I can use this math rule to solve this problem, but it turns out that they want you to realize, oh, I can't use it because it's not continuous at that point. And if you don't catch it, you'll miss it. So let's do another one. Now, if you guys are filling out your stuff on the notes handout that I gave you, then you might want to, you'll have to probably make a new number 1, 2, and 3 for each thing for really to be with the class. You doing this? All right. This is important stuff. Okay. Number 2. G of x is equal to the cube root of x plus 9. So what kind of function are we looking at here? An odd root function. Good. Where are they discontinuous? None. They don't have any discontinuities. So where are they continuous? You could say everywhere, or we could say that. That was easy. Oh wait, since you could probably have to write this. I guess you could probably just title it A, B, and C and maybe reference it back. So what do you guys think about this one? What kind of a function is that? Okay, even root. Where are they discontinuous? They're not. They're continuous pretty much everywhere. Well, they're not continuous everywhere, but where they do exist, they're continuous. Where are they continuous at? All x for which, what? So in this case, what is my r of x? It's x plus 4, right? So I'm just going to put that here instead, and we'll solve. So you could write it like this, or what's another way? If we use interval notation, how would I write that? For all x greater than or equal to 4. No, it's greater than 4. So starting at 4, bracket or parenthesis? Bracket, because it can be equal to, right? And it keeps going on for how long? Forever. Parenthesis. So you could write it either way. Oh, it would be -4. Yes, it would. Thank you. Good obs. Good catch.
Is that number 2?
What do you mean?
What's the solve for number 2?
This is for number 3. Yeah, so for each problem doing these 3 things, we're identifying what the function is, where it's discontinuous, and where it is continuous. All right, let's take a look at, I think, one more maybe? This one's probably the weirdest one, so you see how you guys do with this one. Okay, so obviously this is a tangent function, right? I don't think we need to rack our brains too much on that. It's a tangent function. According to your little sheet there, where are tangent functions discontinuous at? Kind of. What does it say in your paper? All x. All x for which a of x is equal to pi over 2, is it plus pi n? Okay, where n represents any integer. Okay, now in this case, what is my a of x? It's pi x. Good. The stuff in the parentheses over there. Now I need to solve for x because I want to find where is x discontinuous at. So how would I solve for x here? Divide everything by pi, right? So divide by pi, divide by pi, divide by pi. I'm going to write my answer up here because I'm out of space. But we're left with x equals, what would this become? 1/2, good, plus n. And that, what does n represent, you guys? Any integer. And remember, an integer is any, like 1, 2, 3, 4, 5, 6, or the negative versions of that. So let me try to bring this down to earth a little bit for you guys, okay? Because this is a lot of math language here, and I'm not too sure if we're all getting it. So if n is an integer, give me an example of an integer real quick. 3. You don't need to write this, just watch. But if that's 3, what's 3 plus 1/2? 3.5, right? So that means when x equals 3.5, there's a hole in our function. Where else would there be a hole? Well, if you plug in 4, right? So at 4.5, there would be a hole. Where else? 5.5. Where else? 2.5. We can go backwards, we can go forwards. It doesn't really matter. The point is every something 0.5, there's a hole in this graph. Okay? So, where is it continuous? That's a little bit difficult to say. You could say the opposite, basically. All x for which x is not equal to 1/2 plus n. Okay, so if it's discontinuous where x equals 1/2 plus n, it's continuous for all x where x is not equal to 1/2 plus n. Okay, we can't really write intervals because it's infinite. It never stops. I mean, you could do something like this if you wanted to. You could put like dots here, and you could put 0.5 to 1.5. It's continuous. And then from 1.5 to 2.5, it's continuous. And then from 2.5 to 3.5. But that's never going to stop. It's just going to keep going. Okay? So a more inclusive way would be to write that. All right? So the main idea I want you guys to walk away from here is being able to identify where different types of functions are actually continuous and where they may be discontinuous. Okay? So, got a couple here for you guys to practice. I'm going to give you guys, like, I don't know, say like 8 minutes-ish to work on this, and then we'll see what you guys get, okay? Yeah. Number one is rational. Chloe, what were the points of discontinuity on number one? Yeah. One of those is right. So what we do is we take our denominator and we set it equal to 0, and then I suggested to you guys to factor it. That would be this. And then if you set both of those equal to 0 and solve, that's how you can find what would make the bottom equal 0. And so one of them is -2, but what's the other one? So there's your 2 points of discontinuity. Okay, what's our, where would this thing be continuous at then? That's fine. I'm going to say what she said. I'm not going to write it. She said all x for which x is not equal to -2 and -1. That would be fine. If you wanted to write it with interval notation, though, that would mean it's continuous for everything from -infinity up to -2, and then from -2 up to -1, and then from -1 up to infinity. Okay? Let's go ahead and take a look at number 2 there. Zarina, what kind of function is that? You're right. Andrew, what did you get for where the second one is discontinuous?
I got it's continuous everywhere.
It is continuous everywhere. So,
Discontinuous.
so if it's continuous everywhere, that means there are no places where it's discontinuous, right? So you also gave me my answer to the last one, from -infinity to +infinity, or you could just say continuous everywhere. That's fine. That's fine. All right, let's go ahead and take a look at the next one there. Orion, what kind of a function is the third one? Good. It's a log function. And Caitlin, where is this one discontinuous at? Okay. There are no discontinuities. Now you might be tempted to say, oh, that means it's continuous everywhere. Well, it's continuous everywhere it actually exists. But log functions have an asymptote which kind of blocks where they actually exist at. So, James, what did you put for C on number 3? You did not do it. All right. Let's try Pearl. What did you put for C on number 3? Okay. X is less than 2 thirds. I think you're right, but I think it's greater than.
But when you divide this into
If you divide by a negative, yeah. So it's going to look like this. So there you go. So good job, Pearl. That was probably one of the harder ones. So basically, anywhere where this is greater than 0 is where it would be continuous. And if you solve for x by adding 2 and dividing by 3, you get what Pearl's has. So this function is continuous for all x greater than 2 thirds, and that means you could write it like this if you wanted to. Either way is good. Yeah.
Wait. So how did you get 2 over 3?
So this is a log function, right? So if you look at your sheet there, And if you scroll your eyes over to the column where about continuity, you see where it says a of x is greater than 0. This is your a. So what you would do is you would write this and solve for x. Add 2, divide by 3. And you get your 2. The answer to the last one, guys, was no discontinuity and continuous everywhere. Okay? But I will be posting your homework for tonight, and I'll see you guys mañana.